with a 1 at the beginning.
Okay, so if a polynomial p of x has a 0 at x equals a, which means the factor is what? And the factor is x minus a, right? So if it has a 0 at x equals a, that means the factor is x minus a, right? And so the a must be a factor of the constant term in the polynomial, right? So the a must be a factor of the constant term. In p at x. Okay, so if you think about, let's take x minus 3 times x plus 4 is x squared plus x minus 12. Where does the minus 12 come from? These two guys multiplied together, right? So if there is an integral 0, meaning an integer value, right? Integer, so plus 1, minus 1, etc., then it must be a factor of the constant term. So the factors of 12 are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6. And if we wanted to say, well, which one of them is it, then we know that x minus a is a factor if p of a is 0. So remainder theorem slash factor theorem, right? So if we know, or we want to say, if this polynomial has an integral 0, and there's no guarantee that it does, right? But if it does have a 0, which is an integer value, then we know that that value has to be a factor of that constant term. Okay? So let's try one. So what we want to do is we want to factor, and where do we use this? Well, we want to factor x cubed plus 3x squared minus 13x minus 15. Okay? Yeah, we can't factor cubics, right? We can factor quadratics. We know how to factor a quadratic, or find the roots. In this case, factor. So we're going to assume this thing does factor. So we say if x cubed plus 3x squared minus 13x minus 15 has an integral 0, then it is a factor of, now it, referring back to the integral 0, right? You can use it here. Then it is a factor of 15. Well, minus 15, but I'm just going to drop the negative, right? It's a factor of 15. So let's list the possible integral zeros. And sometimes that's what the question is, right? Just list the possible integral zeros. List the possible integral zeros, okay, which we will call P-I-Z. Okay, what are the possible integral zeros? Okay, which means that we want to try P of 1. If P of 1 is a 0, then we know that x minus 1 is a factor. Then we'll do a synthetic division. We'll get the quadratic factor, and then we'll factor that, right? And that's how we do these. And it doesn't matter what degree this is. If it's degree 5, you find a 0. You say, okay, look, this is a 0. I do a synthetic division, knowing that I should end up with a remainder of 0, or I messed up. right? If you don't get a remainder zero, then you're messed up. And then if it's a fourth degree, you find another one. And a third degree, you find another one. And second degree, then you factor it. Yes?
Shouldn't there be an equal zero beside the polynomial?
Why?
Because we have to find the roots of it, so it has to equal zero, right?
I just said factor this, didn't I? Did it say find the roots? Did it say solve? What word do you see there?
Probably.
Factor. As a matter of fact, I can't factor this. That's an equation. I can solve that equation. I can solve it by factoring. But I just want you to factor. Okay? So we can't solve this. We don't know what it's equal to, right? We're going to assume it's y equals, it's, you know, it looks like this, right? Its end behavior goes from quadrant 3 to quadrant 1. It probably has 3 zeros. We'll find out what those are. Its y-intercept is negative 15. This we know because you just put a 0 in, right? But no, the instructions say factor. Okay, so keep it simple. Okay, so what do we want to try? Well, let's try 1, right? I mean, why not 1? So what we're going to do is we're going to go P of 1, which is 1 cubed plus 3 times 1 squared minus 13 times 1 minus 15, which is 1 plus 3 minus 13 minus 15, which is not 0. I don't know what it is, but it ain't 0. It's like minus 26, but or no, it's not. It's minus 20. See, it's not 0.
Close enough.
Okay. Yeah. So it is negative 24, but it's not 0, which means that x minus 1 is not a factor, right? Since p at 1 is not 0, then x minus 1 is not a factor. Okay. Let's try p of negative 1. Okay, so that's negative 1 plus 3 plus 13 minus 15. So we got 16 minus 16, which is 0. Aha, so rejoice. And we know that x plus 1 is a factor, right? So from this, that leads to x plus 1 is a factor. So we are now going to divide the polynomial by x plus 1 using whatever method, synthetic division, that you like, synthetic division. And I know that's a 0, right? So I'm writing that in right now. Okay. So we say the factor is x plus 1. You look in the book, I think they do this synthetic division by adding, in which case you'd put a negative 1 there and then you would add. Doesn't matter. I don't care. I'm not testing you on synthetic division, right? Synthetic division is a tool that we use to, you know, divide. 1, 1, 2, 1, no, 2. Negative 15, negative 15, 0.
Oh my god.
Okay, so the factored form then of x cubed plus 3x squared, right? And I can just read that off of here, right? Constant term, x term, squared term, cubed term, x cubed plus 3x squared minus 13x minus 15 is equal to x plus 1, which is the factor, and x squared plus 2x minus 15. Which gives me x plus 1 and okay, check this. I cannot emphasize this enough. Okay? X squared minus 3 plus 5 is plus 2 minus 15. Okay? Because you get that wrong, then everything from that point on is wrong, right? Now you say, well, the zeros are negative 1, negative 5, and positive 3. I could graph this thing now or get a pretty decent approximation of the graph of this because I know where the zeros are. I know the end behavior. It's going from quadrant 3 to quadrant 1, and I've got a y-intercept. I don't even need to know the end behavior if I know it's cubic, so it goes in opposite directions, and I have 3 x-intercepts of multiplicity 1 and a y-intercept. There's only one way I can draw it. Right? If I try and draw it the other way, it's not going to work. Okay. So there we go. Right? We have the fully factored form of this is, so this whole idea of the integral 0, rational 0 is just to give us a fighting chance, as opposed to just graphing it in our calculator and picking off a 0, which is what you'll do in real. So that was integral. What about rational zeros?
Integral. A over B is a factor of bx.
What are you talking about? What are you reading out of the book or something?
Are you reading out all of those markers on random? Yeah, plus the notice is central.
Okay, so we know the possible integral zeros are what?
Well, plus or minus 1, plus or minus 2. Wait.
Right? But we also know that one of the factors of this thing is going to be of the form, so there may be a factor, there will be a factor, I'll say there will be. But it's really there may be. There will be a factor of the form ax minus b, right? Because we know that we need a 3 leading, so we're going to have one factor that looks like 3x plus or minus something, and then x plus or minus something, and then x plus or minus something, right? We know that the constant terms are going to multiply to give you positive 2, right? So they're likely 1s and 2s. And as a matter of fact, they're plus or minus 1, plus or minus 2, right? If there are any integral zeros. Okay, no guarantee there has to be. But there will also be a 0 of this form. What's the root that goes with this? B over A, right? So if the factor is in the form ax minus b, then the root is b over a, which means that p of b over a will be equal to 0, right? If it's a factor. So given, that factor, if there's a factor of that form, this form, then it's b over a. So in this case, a is our leading coefficient, and b is our constant term. And the factors are therefore of the form plus or minus b over a. Now you get to use b over a because now we know what a and b are, as opposed to just saying, hey, it's b over a, but with no context, right? Now we have context. So, given there's a factor of this form, so these are the possible rational zeros. Okay, so they are factors of b over factors of a. All right, so we need room to do this, right? So let's just go down here. So factors of b, so the possible rational zeros. By the way, integral zeros are simply a special case or a subset of the rational zeros, right? Because they're going to come out in here. So possible rational zeros are factors of the constant term over factors of the leading term Okay, what are the factors of the constant term?
1, 2, plus or minus 1.
Plus or minus 1, plus or minus 2. What are factors of the leading term?
Plus or minus 1, plus or minus 3.
Plus or minus 1, plus. Now we got to put those all together, right? So, let's just do this kind of systematically to make life easier on ourselves. So we'll start with 1 and 1, right? So it's plus or minus 1. So if I want to actually list them all.
There's a lot, though.
Yeah, so the possible rational zeros. Oops. PR.
I think you should substitute
1. Negative 1. 1/3.
Negative 1/3. Oh God.
Negative 1/3. Okay, that's used up the 1 with the 1 and 1 with the 3. So what else? What's next?
2 plus or minus 2.
Yeah, so 2. Negative 2. 2/3. Negative 2/3. Right?
Oh my word.
So I guess we could write this shorter by going plus or minus 1, plus or minus 1/3, plus or minus 2, plus or minus 2/3. Okay? Now, you ain't seen nothing yet. If the number up top is 6 and 15, then you got 1s and 2s and 3s and 6s and 1s and 3s and 5s and 15s. Now, when you do that, put them together, you're going to end up with a lot of repeats, right? Like if they share a factor, if there's a 3 here and a 3 here, you're back to plus or minus 1, right? Because you're going 3 over 3. So you're not going to repeat it. These should be unique. You shouldn't be repeating them. If you get something that ends up being 4 over 6, you've already got it if you've got 2/3. So again, don't repeat it, right? Reduce everything to lowest terms. Don't repeat values. So that everything here should be a unique value, right? So I don't want to see plus or minus 2/3, then a little later on, plus or minus 4 over 6. Okay, because that's just 2/3. Okay, so these are the possible rational zeros, right? And we try those. So let's throw. Now this is we're going to evaluate p of 1/3, right? Which is equal to what was p? 3x cubed, so 3 times 1/3 cubed minus 4 times 1/3 squared. Minus 5 times 1/3 plus 2. So 1/3 cubed is 1 over 27 times 3 is 1/9 minus 4/9 minus 5/3, but let's continue with the ninths. So 5/3 will be 15/9 plus 18/9. So we got 1 minus 4 is negative 3, minus 15 is negative 18, plus 18, so it's 0. Okay.
Genius.
So x minus 1/3 is a factor.
Wouldn't it be? Oh, no, it's 3x. So why couldn't we just use the formula? Just go integral 0.
Yeah, eventually we're going to turn it into 3x minus 1, but just wait. So, yeah, 3x minus 1 is the factor, right? So you could do two things at this point, right? You could say, all right, we found our factor, so I can divide. Now, I'll have to do x minus 1/3. I don't really need long division, do I? 3. What was the 4? Negative 4, negative 5. I mean, look, it's got to come out to 0, so it has to divide. Negative 1/3 times 3 is negative 1. Negative 4 minus negative 1 is negative 3. Negative 1/3 times 3 is 1. Negative 5 minus is negative 6. Negative 1/3 times negative 6 is 2, giving you 0, right? And that to divide in, so... Now, as a matter of fact, if we had made this factor 3x minus 1, then we'd have to do long division. Or we'd have to change the factor to be x minus 1/3, which is the same thing, right? So you could say, oh, x minus 1/3 is a factor. We'll write that as 3x minus 1. I want to do synthetic division. I can't divide with the leading 3 there, right? Because we don't do anything with this. It has to be an x. Right? It's only this that we do stuff with. So you have to change 3x minus 1 back to x minus 1/3 and do a synthetic, or you could do a long division by 3x minus 1. So me, lazy, I'm just going to do the synthetic by x minus 1/3. So, and I get 3x squared minus 3x minus 6. And I'd say, wait a sec, 3 is a common factor. I'm going to multiply everything by 3. Sorry, I'm going to factor out the 3 and get x squared minus x minus 2. And I'm actually going to put the 3 into here, right, which gives me the 3x minus 1. See, now I got rid of the 3 and I got rid of the 1/3. And we'll factor this, which has to be what? X minus 2 and x plus 1. X squared plus x minus 2x gives me minus x, yes. Okay? And you'll always, 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 gotta say at least a dozen times because half dozen is never enough. Always, 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 always check your factorizations.
No. Yeah, last time I lost like 4 marks. Yeah.
Okay? So, that means that 3x cubed minus 4x squared minus 5x plus 2 is equal to 3x minus 1, x minus 2, x plus 1. Okay, that's the factored form. So what are we doing? Basically recap. We say the possible rational zero theorem, which includes integral zeros, right? Because if your leading term is a 1, then you just end up with plus or minus factors of the constant term over plus or minus 1, which is just integral values, right? Just the plus or minus factors of the constant term. If I'm doing one of these for reals, as in I don't have a calculator with me and I'm actually doing this, then I would check for integral zeros first before you get into checking for rational zeros, because A, it's likely there will be some integral zeros, and B, if there are, it's a heck of a lot easier than, you know, and because you'll have so many possible values that you could substitute in, right? So when you're looking at possible zeros, there may be 15 or 20 or 30 possible zeros, right? Especially rational zeros. That's why basically you generally want to graph this, find an integral zero, but then you got to do the following, right? You have to show that it is a zero by evaluating p at the value a, say that it's 0, then from that state the factor. Since p of a equals 0, then x minus a is a factor. Do a division by x minus a. If you're going to do long division, get out your own scrap paper and do it on there. If you're doing synthetic, there's probably room to do that. So do a synthetic division. Get it down to 1 degree less than it was. If it's 5th degree, you get it down to 4th degree. Then you show another integral 0 and get it down to 3rd degree. Then you show another integral 0 and you get it down to 2nd degree, and then you factor that as a quadratic, right? Which we know how to do. Yes? Yes? I don't know, but I'm sure Google could tell you. So you can't, there is a formula for factoring cubics, and there might be one for quartics, but there is nothing for above that, as was proved by some dead white guy mathematician. So,
Always white, isn't it?
yeah, I know. I mean, it's let me put the recording off here. I think we're done.